Welcome to qnawire.
For this question, we're trying to show that if G is connected, then it is possible to remove vertices to disconnect G if and only if G is not complete. So one way to approach this problem is to show that if G is complete, then we cannot remove vertices to disconnect G. And alternatively, if G is not complete, then we can remove vertices to disconnect G, right? Doing so, essentially showing that these two parts are both true will give us the information needed to draw the conclusion of problem 51. So first off, let's assume that G is a connected graph on n vertices, right? So if we remove one vertex, then we'll get a connected graph on n minus 1 vertices, right? Because if we remove one vertex, then the degree of all the remaining vertices goes down by exactly 1. So all n minus 1 vertices will have degree n minus 2, because the edges connecting all possible pairs of these n minus 1 remaining vertices will still be intact. There will still be edges. So basically, if we removing j vertices, then, right, gives us a complete graph on n minus j, on all n minus j remaining vertices. And so this goes on forever. And so we cannot, in conclusion, we cannot disconnect G by removing vertices, because no matter how many we remove, we will just get a complete graph on the remaining vertices in the graph. So the first part of the statement is complete, right? We've shown that if G is complete, then no matter what vertices remove, G will always remain connected. Now, if G is not complete, so this is the second part of the problem. If G is not complete, then there exists a pair of vertices UV and G such that UV is not an edge, right? Because if there was an edge connecting every pair of distinct vertices in G, then G would be complete. Because G is not complete, we can find such a pair, UV, such that UV of vertices, such that they're not connected by an edge. Now, the way we remove vertices in order to create a disconnected graph is just remove all vertices but U and V, right? Because if we do so, we will be left with two vertices and no edges, and this is not a complete graph. And so this will result in disconnected G. And for that reason, if G is not complete, we can remove vertices to disconnect G, right? We've proven both these two statements, and because that's all we need, we're done. The problem is done. So in conclusion, we just split the problem into two parts. One was proving the statement regarding a complete graph. One was proving a statement regarding a non-complete graph. Since we proved both of those, our